So you just have a look at page 29 of your worksheet. This one is November 18 P42, all right? So for November 18 P42, for that particular question, they ask you to state what is meant by a photon. Now, a photon is just a packet of energy of electromagnetic radiation, so it's usually worth 2 marks. The moment you say it's a packet of energy, it's 1 mark, and its electromagnetic radiation is another mark. Okay, so this is something that we've done quite often before this. Now, in part B, they ask you to describe the appearance of a visible line emission spectrum as seen using a diffraction grating. Okay, now your diffraction grating is kind of similar to that of a prism too. Okay, the example in the notes, I use a prism, but in the question here, they say using a diffraction grating. They are actually both the same in the sense that they can spread colors across a screen. Okay, so if you want to spread certain colors across a screen, you can use a prism, you can use a diffraction grating. Okay, so here they want you to describe the appearance of the visible line emission spectrum. How does the emission spectrum actually look like? It appears as a series of colored lines on a dark background. Okay, here I did not write as a series of colored lines now. You can actually just write it as colored lines on the dark background. That one will also be sufficient. Okay, so this is part B. Okay, then next part, you look at part C. Okay, so I'll just clear this thing off. So in part C here, they say that the lowest electron energy levels in an isolated hydrogen atom are shown here. An electron is initially at energy level negative 0.85 eV. State the total number of different wavelengths that may be emitted as the electron de-excites or loses energy. So right now, your electron is at energy level 0.85, negative 0.85 eV. This one, I should just mark it out on your diagram with a different color, is actually this line here. Okay, so they are asking you, if it were to de-excite or lose energy, meaning you say it's trying to go down to a lower energy level, what are the different wavelengths that you can get out of it? You recall just now I mentioned to you, as your electron goes down to a lower energy level, it will tend to emit a photon of a certain energy, and the energy will be equal to the difference in your electron energy level. Okay, so the question now wants you to state how many different wavelengths or how many different transitions downwards can you get. So you look at the workings already stated below here. If you are at negative 0.85, you want to go down all the way to negative 13.6. What are the different ways in which you can go down? So you can go down in this step, and this step. You can also go down in this step, followed by this step, and lastly this step. Okay, so these are 6 different unique transitions downwards. Okay, so you have 6 different unique transitions downwards, 6 unique ways in which your electrons can fall back to a lower energy level. That will correspond to 6 different wavelengths. Okay, so your answer here is 6, right? Because each of these, as it falls down, will emit photons. Okay, so the photons would have different energies. They will also have different wavelengths here. Okay, because energy of photon is equals to hc over lambda. All right, so you have 6 different wavelengths, then that one should be okay. Now then you move on to the next question. This one is actually on your photoelectric emission already. So you move on to the next question in the next page. They mentioned to you that photons resulting from electron de-excitation from negative 0.85 eV energy levels are incident on the surface of a sample of platinum. Your platinum has a work function energy of 5.6 eV. Okay, so determine the maximum kinetic energy in eV of a photoelectron emitted from the surface of the platinum. So let's imagine right now that you have a platinum surface. This is your platinum. Okay, so let me just write it out. This one is your platinum. And then you have the photons coming over from the de-excitation of your electrons from the previous case. Okay, so you have all these different photons coming in here, right? So let me just try to write it out. So you already stated in the previous question that as the electron de-excites from negative 0.85 all the way to the ground state, there are like 6 different wavelengths, 6 different photon energies. So which one do you want to choose here? Okay, so for the case that you have right now in part 1 of your question, they want the maximum kinetic energy of photoelectron emitted from the surface of the platinum. Okay, so here, to get the maximum possible kinetic energy, this one, to get maximum kinetic energy of electrons, KE of electrons, what you learned from the previous lessons was that if you were to get maximum KE of electrons, the electrons must be emitted from the surface. Okay, maximum kinetic energy of electrons only come about when the electrons are emitted from the surface itself, rather than deeper below the surface. So if you consider this fact itself, that's the reason why you have your photoelectric equation, is to take into account this particular situation for electrons emitted from the surface. Now, another thing to note also is that to get the highest possible KE of your electron, to get the maximum possible KE of electrons, the photon energy absorbed should be as high as possible. Okay, so what you could also say here is that the photon energy absorbed must be, rather than saying must be, I should just say should be. Okay, the photon energy absorbed should be maximum 2. Okay, so these two factors will get you your maximum K of electrons. They must be emitted from the surface, and you must get the maximum photon energy. So in your case here, if you look at the electron de-excitation from the previous page, you want to get the one that gives you the largest photon energy. Okay, you want to get the photon with the largest energy. That would mean that it has to travel the largest distance between electron energy levels. So if you started off at negative 0.85, you need to go all the way to negative 13.6, which is basically this electron here. The photon that you emit out of it, this one is photon with maximum energy. Okay, so you want to take this photon and you want to plug it inside your photoelectric equation. So if you now look at the workings from there, you will take the one with the largest photon energy. You take the difference between the electron energy levels is 13.6 and 0.85. You take the difference, you will get 12.75 eV. Then you plug it inside your photoelectric equation, where you say that photon energy is equals to work function plus KE max. So photon energy is 12.75 eV work function is 5.6 eV. Your KE max is therefore 7.15 eV. Okay. For your photoelectric equation, you can use the general form of it instead of writing it as HF equals to 5 plus KE max. You can use the general form of it. All right. So you will get your KE max as 7.15 eV. So if you have electrons here right now, they will get emitted and they will have maximum KE. All right. So in part 2, the wavelength of the photon producing the photoelectron in part 1. So this is related to your previous question. They want the wavelength of the photon that you use that gives you maximum kinetic energy in part 1. So you already know that the energy of your photon is 12.75 eV. So you use back the equation E is equals to hc over lambda. Lambda is hc over E. Your Planck constant is 6.63 times 10 power minus 34. P of light is 3 times 10 power 8. And your energy is 12.75 eV. You need to change it back to joules. You need to multiply with 1.6 times 10 power minus 19. Because 1 eV is 1.6 times 10 power minus 19 joules. So your final answer would be 9.75 times 10 power minus 8 meter. Okay, so this is one question here. Right, next question you can look at is page 18. Okay, so let me clear all the writings here. Next question should be page 18. It is June 17, P41. Okay. So for this question, this is on emission spectrum, absorption spectrum. You have a beam of light that consists of a continuous range of wavelengths from 420 nanometer to 740 nanometer. The light passes through a cloud of cool gas as shown in the figure below. For part A, the spectrum of light emerging from the cloud of cool gas is viewed using a diffraction grating. Explain why this spectrum contains a number of dark lines. Okay, so what you have is incident light. Sorry, I should use this color. What you have is incident light. It passes through a layer of cool gas, which is this one here. So after that, it emerges. Okay, it emerges in the same direction. But somehow or another, what they mention is that they go and put a diffraction grating here. They're going to put a diffraction grating here. And what they saw after the light passed through your diffraction grating was that you have a spectrum with dark lines. Okay, what you see from here is a spectrum with dark lines. This is already referring to your absorption spectrum. Okay, they want you to explain why did you have the dark lines in the first place. So this one was actually explained in your notes. You can actually just reproduce back some of the points there. So what you could say in the first place is that the electrons in the gas atoms over here interact with the photons of light from over here. The photon energy of light there causes the electrons inside your gas atoms to move to a higher energy level. Okay, the photon energy that is absorbed is equal to the difference in your electron energy levels. When the electrons return to the original energy levels, these photons are emitted in all directions, causing the dark lines. Because they are no longer in the incident direction. Okay, the incident direction is this direction. Okay, your photons of different colors, different wavelengths, they all got emitted elsewhere. Going here, going here, going here, going here, or going here. Okay, so the electrons, the photons that you have here emitted in different directions are the ones that cause your dark lines in the first place. Your question here has 4 points allocated to it. So each statement here is actually worth 1 mark in itself. Okay. So this one is a pretty standard question that does come out. All right. It will be a good idea to memorize the standard answer here. Okay, so if this is okay, then you move on to part B. I'll just clear off the writings on the screen. Now in part B, they mentioned to you that some of the electron energy levels of the atoms in the cloud of gas are represented in this figure here. All right. So you have those energy level diagrams there. So in part 1, in the following page, they ask you to calculate the photon energy in EV of light of wavelength 740 nanometer if light of wavelength 420 nanometer has photon energy of 2.96 EV. Okay, so if light of wavelength 420 nanometer has photon energy of 2.96 EV, what is the photon energy in EV of light of wavelength 740 nanometer? So this one, you can do it in 2 different ways, using a ratio method or just direct calculation. If I wanted to do it using a ratio method, that one would be the ones that I've already written in pencil here. You could say that because you're dealing with photons, E is equals to HF or Hc over lambda. There are certain things that are constant there. Time constant and speed of light are constant. That would mean that your photon energy is inversely proportional to your wavelength. So right now, you can say that E2 to E1 is the same as lambda 1 to lambda 2. E2 is what you want to find right now. It is representing the wavelength of 740 nanometer. So if you sum out the values, lambda 1 is 420 nanometer, lambda 2 is 740 nanometer, multiply with the energy of your first photon of 2.96 EV, you're going to get 1.6 EV, 1.68 EV as your answer. This one is if you use ratio, okay? But if you don't want to do this, you can also use direct calculation like the ones that's being shown here. Okay, you can straight away just use E equals to Hc over lambda, sub in the Planck constant, sub in your speed of light, sub in the wavelength. Eventually, you get the answer in joules. Then after that, you divide by 1.6 times 10 power minus 19 to change it to EV. You will get the same exact answer too. If you do this one, this method here, you actually had no use for the first statement here at all. All right, the first statement here is only useful if you're trying to do it in this method here. Okay, so if that is all right, then you move on to the last question. Now in part 2, use data from 1 and your answer in 1 to show on figure 11.2 the changes in energy levels giving rise to the dark lines in A. Okay, what are the possible energy changes that will give rise to your dark lines in A? Okay, so one thing to note here is that when in your exam questions, they ask you to indicate the energy level transitions for absorption spectrum or emission spectrum. Generally, this is what you need to remember. If it's emission spectrum, usually when you want to indicate the electron transition, the lines tend to point down because it's emission. Okay, but when you're talking about absorption spectrum, and they go and ask you some sort of energy transitions related to that, the lines tend to point up because it's absorption. Okay, so if you look at the answer now here, the answers tend to point the arrows upwards. Okay, there's a reason for it, because it's an absorption spectrum. You don't draw it downwards. Downwards is for emission spectrum. Okay, so the arrows that are drawn here, why is it drawn that way? Can't you just draw them randomly? Okay, there's a reason for that. That one is actually related to an earlier part of your question just now. If you read through your question, they told you that you have a beam of light consisting of a continuous range of wavelengths from 420 to 740 nanometer. There is a range to your wavelengths here. Okay, so maybe I should just write this up here. There is a range of wavelengths, hence there's a range of energies. There is a range of wavelengths, hence there is a range of energies to consider. Okay, if you now look at the diagram below here, okay, since your wavelength of light that you use is from 420 nanometer to 740 nanometer, the energy of photon absorbed, your delta E, will be between 1.68 eV to 2.96 eV. Okay, your electron transitions must be within this energy range. Okay, if you try to draw your electron transitions, the energy involved there must be within this range. Now, where do you get 1.68 and 2.96 eV in the first place? It's actually from what you did earlier already. They told you 420 nanometer is 2.96 eV, and then they asked you to find how much is 740 nanometer. You found it out as 1.6 eV, right? This is the values that you got earlier. And the question already did give you a hint. Use data from 1 and your answer in 1. Meaning to say you use this. Okay. So your electron transitions upwards in absorption spectrum must correspond to those energies. So the lines that will give you an energy value within that range is actually just these three. This is 1, this is 2, this is 3. Okay. Any other transitions, if you do by trial and error, they are actually not within this given range that you have here. They're either below it or they're either above it. So for example, for the first, second, and third transitions that you have here, if you want to try and see whether the energies are within the range, the first one was from 3.4 to 1.5. The difference is 1.9 eV. The second one is from the second one, which is this one, is from 3.4 to 0.85. The difference is 2.55 eV. And then the last one is from 3.4 to 0.54. The difference is 2.86 eV. You see that this is still within the range here. Okay, so that's why it's just these three values. All other transitions are either below or above the range, so you don't draw. Okay, so that's for page 18. Then let me just clear this thing up and move on to page 16 for you. Okay, so next question that you can have a look at is actually page 16. Okay, have a look at page 16. This one is March 2017 P42. Okay, so for this question here, let me zoom in a little. State what is meant by a photon. We just did something similar just now. A photon is just simply a packet or quantum of energy of electromagnetic radiation. So no issues there. And then in B, you have light in a beam that has a continuous spectrum lying within the visible spectrum, visible region. The photon of light have energies ranging from 1.6 eV to 2.6 eV. You again see that there's a range of energies here. The beam passes through some hydrogen gas. It then passes through a diffraction grating and an absorption spectrum is observed. So they specifically told you that you observe an absorption spectrum here. Okay, so in the first part of the question, all the light absorbed by the hydrogen is re-emitted. Explain why dark lines are still observed in your absorption spectrum. So to illustrate what is happening here, you could kind of think of it as this. This one is your incident light. It passes through a layer of cool gas or cool hydrogen gas here. So after that, that light emerges from here. This is your emergent light. And then after that, you try to pass it through a diffraction grating. This one, you try to pass it through a diffraction grating. And after that, the diffraction grating will try to split up your light into separate spots on the screen. So say this one is your screen here. Okay. So what you see on the screen, as mentioned by your question, is that you see your absorption spectrum. You get missing lines, missing dark lines on a colored spectrum. Okay, so they say that all the light that you had in the hydrogen is re-emitted. Okay, so your photons of your incident light went into your hydrogen gas. The photons are emitted. The photons are absorbed by the atoms inside your hydrogen gas. The electrons excite, and then after that they excite and emit out your photons. So they ask you why the dark lines are observed, even though the photons are all re-emitted back. The reasoning for that is because your photons are emitted in all directions or random directions. Okay, so you could think of it as this. They are re-emitted, but they are re-emitted like this. Okay, so these are the photons that cause the dark lines in the first place. They are no longer inside your emergent light. They are no longer inside your incident direction. So your answer, you can just word it in one simple phrase, because the lights are emitted in all directions. Or you want to word it a different way, you can say that only part of the emitted light was in the direction of the beam. Okay, so that one is one. Then you move on to part 2 here. I'll just clear off the screen. Now, in part 2 of your question, some of the energy levels of an electron in a hydrogen atom is as illustrated in the figure below. The dark lines in the absorption spectrum are the result of the electron transitions between the energy levels. On figure 10.1, draw arrows to show the initial electron transitions between energy levels that could give rise to the dark lines in the absorption spectrum. Okay, so draw arrows that could give rise to the dark lines in your absorption spectrum. So one thing to note here is that for the light that you had used before this, that cause your absorption spectrum, they have a certain energy range. Okay, so you can see here, just like before, there is a range of energies. So your electron transitions must be within this range of energies. Okay, so your energy of photons must be between 1.6 to 2.6 eV. All right, the difference in your electron energy levels must be between these two values. So because it's an absorption spectrum, the arrows you draw must be outwards. Okay, that is actually specifically indicated in your marking scheme point. All right. What are the transitions? It's actually just these two. This is the first transition. This is the second transition. It will be between 3.4 to 1.51, and it will be between 3.4 to 0.85. Okay, these are the possible transitions. If you want to calculate out, you could quickly calculate it out also. 3.4 minus 1.51 would give you 1.89 EV for the first one. And then for the second one, 3.4 minus 0.85 will give you 2.55 EV. So they are still within the range here. All right. All other transitions are either below the range or above the range, so you don't draw those. Okay. Then after that, if you're okay with that, move on to part 3, which is the last part of your question. Calculate the shortest wavelength of the light in the beam. Okay, calculate the shortest wavelength of light in the beam itself. Okay, in the beam of light. What is the shortest wavelength of light in the beam? So what you remember is that that beam of light had a range of energy between 1.6 to 2.6 eV. Okay, so the one that will give you the shortest wavelength is the one with the largest energy, right? Because what you remember is that E is equals to hc over lambda. E is inversely proportional to wavelength. So if your lambda is minimum, your E should be max. So you want to get the maximum energy that is present inside the light. It should be 2.6 eV. Okay, so you use equation E is equals to hc over lambda. The energy you use is 2.6 eV. Remember to change it to joules. Then sub in all your standard constant, the Planck constant, the speed of light. Eventually, you'll be able to find out the wavelength. It will be 4.78 times 10 power minus 7 meter. Okay, so that is it for this question. All right, so with this, we're done with absorption and emission spectrum. The last part I need to go through with you is actually your de Broglie wavelength.